So let us continue talking about sets, and now we're going to move on and use some important proofs to show relations between sets. First of all, recall that we start talking about sets and the operations between sets. A set is a collection of objects. Then in this group map, you're interested in having the collection of numbers or some numbers that satisfy some conditions. We said that we can form the union between sets. Let U be the universal set. Let A and B be two sets. Remember that the operations that we introduced were union, which defines as the set of all elements like X, such that X is in A, or X is in B, or X belongs to both of them. We introduced the intersection. A intersection B is the collection of all X values such that X is in A and X is in B. Remember the keywords that you're using here, or for union and for intersection. We talked about the difference between two sets, and remember that the subtraction, the difference, is not commutative. So A minus B is all X values such X is in A and X is not a member of B. And remember that this guy in general is different from B minus A. We also talked about a complement of a set, A prime, A bar, or AC, which is defined as all elements that belong to the universal set, and they are not in set A. X is not in A. Very good. So now we're going to use the direct definition and prove some relations between sets. For example, I'm going to write this statement and try to check to see if it's true or not. So this is my statement. In this statement, I have the following. The statement says, well, for all sets like A and B, my statement says the intersection between A and B is always a subset of A, and the intersection between A and B is a subset of B as well. So I have a statement here. How do I accept this statement? You might say, well, I can use Venn diagram to prove this. But since we're in discrete math class, we're interested in writing the official proof. So let us try to write the proof here. Let us try to prove this statement. Very good. So how do I prove A intersection B is a subset of A? How do I prove that? I'm going to go back to the definition of being a subset. Well, we learned this at the beginning of this class. Recall that. We say, for example, set A is a subset of set B if and only if we take any element in A, that element lands in B. for any element like X in A, we conclude that X belongs to B. So this is a definition. We use this definition to define being a subset. So now we want to show that this set is a subset of this set. To prove A intersection B is a subset of A, we take X in the intersection in the smaller set, and we show that, so this is our goal, X belongs to A. So put a question mark here. We're trying to show X belongs to A. Let us start by using the definition. Using the definition of intersection. Okay. How did we define the intersection? This guy says, hey, X belongs to A intersection B, since X belongs to A intersection B, by definition, X belongs to A, and at the same time, X belongs to B. Well, take a look at this. Using the definition of intersection, I just showed that X is a member of A. So since X is in A, we're done with the proof. Since X belongs to A. And this is what we tried to prove. So we are done. X belongs to set A, and that element was taken from A intersection B. So we just proved that the intersection between A and B is always included in A. With the same argument, you can show that the intersection between A and B is always included in B as well. If you think about the intersection of two sets in Venn diagram, if you have set A and set B, recall that the intersection is the set of all common elements. This guy is A intersection B. As you can see, it's included in set A, and also it is included in set B. So now this statement is changed into a theorem.